Yeah, so I was saying, imagine if you had your house wired with silver silver cables, how much would it cost you? It would probably cost more than it would cost you to build the house, simply because of the price. So that's why copper is more commonly used, because it's fairly relatively cheaper and much cheaper than silver. So silver is used for jewelry and high quality cutlery. You can see the forks and the spoons there. It's also used for currency coins, though we don't see these currency coins anymore. And it's also used as a sports trophy, and also used in mirrors as a reflective metal. No, not all mirrors, I can tell you. But anyway, those are its uses. It has a melting point of 961 degrees Celsius. I don't know if we ever had silver coins in Zambia, but I don't think we've ever had. Maybe in the past, maybe in the 60s, 70s, but definitely not in the last 20 years, no. Okay, we come to gold. Gold is dense, soft, shiny, malleable, and ductile metal. So pure gold has a bright yellow color, and luster traditionally considered attractive. However, of course, in terms of color and appearance, different types of gold, depending on which part of the earth it was mined. In some places, pure gold looks more of brownish color than bright yellow. So South African gold is bright yellow, probably the brightest in the world. So gold resists attacks by individual acids and it won't tarnish. So when your gold is original, whatever, in most environments, it does not tarnish. So that's how you know whether your necklace or your ring is original or not. When you do some washing or you do the dishes, it starts to look dull and starts to tarnish. Just know that it's not original. It won't tarnish, it won't discolor, it won't crumble, and it won't be affected by most solvents. Use jewelry also in computers as a conductor. Okay, it's also used as a conductor in computers and used for its reflective powers to protect satellites, as you can see here in this satellite here. Melting point is 1,337 degrees Celsius. Move to magnesium. Magnesium, we've heard about it, I'm sure, so many times. Probably seen it so many times. We also mine it here in Zambia. In the Okla province, I know is one place that we have a tremendous presence of magnesium. Fairly strong, silvery white, lightweight metal. It's 1/3 lighter than aluminum. It's actually lighter than aluminum. However, it slightly tarnishes when exposed to air. And in a powder, this metal heats and ignites when exposed to moisture and gets into the white flame. So in short, it's used in these beautiful fireworks that we see displayed. These are mainly the powder. Powder that is used is the magnesium because it's highly explosive. It ignites when exposed to moisture and burns with a white flame. So it's used in pyrotechnics, which is what we call fireworks, and it is alloyed with other metals to make them lighter and more easily welded. Okay, like in this case, you can see someone welding. So it's used to make other metals lighter and more easily welded. Melting point is 648 degrees Celsius. Brass here, like we said earlier, is a mixture of copper and zinc, copper being the main component. And the color of brass varies from dark reddish brown to a light silvery yellow. Stronger and harder than copper, but not as strong or hard as steel. Okay, harder than copper, but not as strong as hard as steel. So you add You are adding zinc to copper in order to enhance strength, okay, in toughness. That's why you are coming up with this alloy. So when you come up with an alloy, you can't come up with an alloy. You can't mix two metals just to get something of poorer quality, for example, in terms of strength and toughness. Usually those are the two things that we're looking for. So when you're going to come up, we're going to mix two metals, you're trying to achieve or trying to enhance a positive property from any of them. So in this case, in case of brush, you're trying to enhance strength and toughness. That's why you're adding, one of the reasons why you're going to add zinc, because combines this, when you combine these two, what is enhanced here is the strength. So it's not as strong or as hard as steel, however, but it is easy to form into different shapes, a good conductor of heat, and generally resistant to corrosion from salty water. Again, here, resistance to corrosion from salty water comes from the component of zinc, isn't it? Because zinc is a highly non-corrosive metal. Brass is used to make water fittings, screws, radiators. I'm sure you've seen screws of this color. Also, screws, radiators, musical instruments, cartridge casings for firearms. So it's also what is used for cartridge cases for firearms. Okay. And also the other reason why we call the brass band, it's called the brass band because of the brass instruments. These instruments, the musical instruments, are made from brass. That's why we call that band the brass band. So please, next time, now that we're doing material science, next time you see a metal that looks like yellowish, brightish, you don't just call everything gold. Okay, at least now you should be able to tell the difference. We come to bronze. Bronze is a metal alloy consisting of primarily copper and usually with tin as the main additive. Hard and brittle. And it has a high resistance to corrosion. So it's hard, brittle with a high resistance to corrosion. This property is enhanced by the presence of what? Of tin, because tin is highly resistant to corrosion. So it's used as ship propellers, underwater fittings, and also for statues and medals. So you need it for underwater fittings, isn't it? Why? Because of its high resistance to corrosion. And when you're looking at water, salty water, it's a corrosive environment. And you have the statues there, and you have the medals made out of bronze. When you talk about the bronze medal, the silver medal, and the gold medal, when it's bronze, this is what we're talking about. Bronze is basically just an alloy of copper and tin. Are we together so far? Mutumba, are you still there?
Yes, madam, we are following.
Okay.
We are following.
Okay, that's good. Okay, so we come to solder. It's a physical metal alloy used to join together work pieces and having a melting point below that of the work pieces. So it's important that it has to be a temperature below that of the work pieces. Otherwise, you find the work pieces melting before the solder itself, which is not what you want. It's an alloy of lead and tin. Okay, solder is made out of lead and tin. Okay. So as you can see here, it's used in electronics. Usually when you are fixing your power bank for your laptop, for example, if the cables in a cut, you need a soldering material to fuse back those tiny cables. It's also used in plumbing. As you can see here, there's a leakage somewhere and soldering is done just to cover up, close up the leakage. It's also used in jewelry making. There's a lot of soldering there when they're making your chains, combining those rings to make up your chain. You need soldering to be done to them. It's also just generally used in repair processes where metal parts cannot be effectively or safely welded. Melting point is also quite low. It has to be low because you need it to be lower than the metals that you're actually using. So which is in this case 200 degrees Celsius. Okay, so under ferrous and non-ferrous, it's that easy. It's not difficult. So what I'll repeat again, what you need to know is weight, and if it's an alloy, you need to know the alloy, what it's made of. For like soda, if you know soda is made out of lead and tin. Brass, you should know what brass is made out of. Bronze, for example, know what bronze is made out of. So just generally, the general properties plus general uses, that's all that is needed from you to know. We'll move on, or are there any questions?
No.
Everything is fine, clear? Okay. Okay, so now we move on to ceramics. However, okay, we'll try and work with this slide. I have another presentation for ceramics that I feel is better than this one, but we can still wait for this one to give us a general overview. So what are ceramic materials? These are non-crystalline silicates containing other oxides such as calcium oxide and so on. There you have the aluminum oxide which influence the properties. Examples include containers, lenses, fiberglass, etc. So they contain the metal and the non-metal ceramic materials. So under ceramic materials, this is the wide family. There are glasses here. You have just simple glasses like the ones that capillary glass used to make. And you have your glass ceramics, like the ones that your mug cup is made out of. Then you have the clay products, structural clay products, and the whitewares. The whitewares here are your breakable plates, your side plates. This is where they fall under. Then you come to refractories. Refractories, that's the bricks that are the lining, the inside lining of a furnace or a kiln, an industrial kiln or an industrial oven. It usually has the lining of small bricks inside. So those small bricks have to be made out of material that has a very high melting point, isn't it? Otherwise, it would melt together with the contents inside your kiln or your oven. So those small bricks that are inside the lining, that make up the lining of your reactor or your kiln, they are called refractories, and they're usually made out of ceramic material. So you have fire clay, silica, basic, and special kinds of refractories. Then you have the abrasives, the cements, and advanced, what are known as advanced ceramics. So this is a whole family of ceramic materials. They're quite wide. Quite wide. So even fiberglass also is included under ceramic materials. So the two prime assets of these materials are their optical transparency and the relative ease with which they are fabricated. They're not very hard to fabricate. And a lot of them are actually transparent. When you look at glass, glass is quite transparent. So those are the ones that are needed, having optical transparency. However, with refractories, of course, this is another important class of ceramics. Like I said, these are furnace linings for metal lining, glass manufacturing, metallurgical, heat treatment, and power generation. That's where you find these refractory materials being used in high temperature works, places where you are dealing with very, very high temperatures. So the salient feature of these materials includes withstanding high temperatures without melting or decomposing, as well as providing thermal insulation. So they're also good insulators. So if they're good insulators, it means that they are not conductors, they're poor conductors of electricity. So we come to cement and concrete. Does cement conduct electricity, Khaled?
No, it doesn't.
Doesn't, huh? Yeah, so cement and concrete are used in construction on a large scale, equal only to structures, steel, brick, and wood. In short, cement and concrete are very widely used. I wish I had the figure for Zambia, just the amount of cement that we use in a year, in a month. There are tons and tons of cement that we use just in a small country like Zambia. Now imagine places that have large scale industries and construction, the amount of cement that they consume as a country, very high. What is cement made out of? Cement is also a ceramic material. It's a mixture of a combination of lime, calcium oxide, silica dioxide, and aluminum oxide, which sets when mixed with water. So it sets, so it hardens when mixed with water. And concrete is sand and stones, aggregate, sand and aggregate held together by cement. So concrete is basically just a mixture of sand, stones, which are held together by cement. While cement is a combination of lime, silica, and alumina. So coming to abrasives, abrasive ceramics are used to wear, grind, or cut away other material which is softer. I talked about the abrasion term, I think, earlier. I hope we all understood. So what properties do these abrasive materials have? They are hard or wear resistant and should be able to withstand high temperatures when in use. Examples of abrasive ceramics include silicon carbide, tungsten carbide, aluminum oxide, or corundum as it is used, and as well as silica sand. These are abrasive ceramics. So like I said, this particular slide has ceramic component is quite brief, supposed to expand. And I'll share with you some more material on it concerning ceramics. I have it, I think, also in soft copy, as well as hard copy. I think let's not get to polymers. I think we've consumed enough material up to this point. So ceramics, I usually ask for the definition, what ceramic materials are, and some examples. If you can give me examples of ceramic materials, or under the classification, examples of any classification that you know or that you remember under ceramic materials. What else do I usually ask? Anyway, just the basics, because I understand that, as you can see, it's quite broad. And I wouldn't want to punish you for you to study all these and know the properties and come and study all these and know all these. It's quite involving because it involves this compound a lot. But I'll just probably say for the main components of glass, for example. I usually ask that question. So I don't expect much from it, but just a general overview to be able to understand what ceramics are and their general uses, and cement, be able to know what cement is made out of, what glass is made out of here, and just any, for example, ask any 3 types of ceramic materials that you talk about. White wares, we talk about even the refractories, so that's basically just enough. Any questions so far? Are people sleeping or they've just understood? Angel.
I'm just trying to follow up what you were talking about, especially on non-ferrous metals.
Okay.
After you ended on silver, I think there was a hiccup there. So I don't know whether the continuation from silver goes to brass, bronze, and solder.
Yes.
Or is there any other that I missed?
Silver and the non-ferrous. After silver, went to gold.
Yes. Gold.
Yeah.
Okay.
Magnesium. And then we came to the alloys, brass, bronze,
okay,
and solder.
Okay.
Yeah.
Thank
Those
you.
are the ones that we can. And I'll still share this presentation with you, so you'll be able to go through it. It's an easy one.
Okay.
And the material is easy to understand.
Thank you.
Doc.
Yes.
And on the when I compare the properties of silver and gold, I tend to believe that gold must be a very good conductor of electricity as well. Would that be true?
Yes. Most metals are good conductors of electricity, by the way. Yes, so most metals are able to conduct electricity with ease. Remember what we talked about when we talked about metallic bonding and just metals generally metals, what happens? They have a sea of electrons. They have a sea of, so what happens with metals is that, remember the shells, the shells where you have your electrons, isn't it? You have the outer shell, the inner shells. So with metals, the outer shell, those electrons that are found on the outer shell, maybe there'll be two, for example, usually 1, 2, 3. Yeah? In the case of copper, it usually has a valency of 1. So you have your copper electron there, isn't it? It won't be stuck in the shell. It will form, the electron will be roaming, it will be free roaming. It's a free ranger. So you have this atom, the electron, the outer electron is not attached to it, it's roaming freely. The other one atom, so you have millions of atoms in a small piece of copper. And all the outer electrons are just roaming around, okay? In a sea of electrons, as we call it. So this particular sea of electrons is what makes it easy when for that metal, for copper in this case, to conduct electricity, because it just passes the same electrons are the ones that will conduct this electricity. So they are free roaming anyway, so they are available, in short. Maybe that's to use layman's language. It means they're available for conduction of electricity. It's easy for them to conduct. So that happens with most metals because they have the electrons, the outer shell freely roaming within the metal. So gold also is a good conductor of electricity, but price, the cost issues are what restricts some of these metals from being widely used. So like I said, imagine if you had your wiring in your house made from gold metals, gold cables, how much would that cost? That's like, it's unrealistically expensive. So that's why we stick to copper, because it's more affordable. Any other questions or clarifications? Okay, if there are no other questions and clarifications, I think we can call it a night. I know because you have to get to work tomorrow, so at least you can rest.
Doc, I wanted to find out something about soldering.
Okay.
Soldering, I understand it's used mostly for joining one or two different parts of metals.
Yes.
Does that mean that it's good at diffusion? I mean, the diffusion property, is it very good or high or wrong? Thank you.
Okay, what do you think? Anyone to respond to that? What does the class think? First, basically, when you're looking at soldering, how's your understanding? Just look at from this photo. What properties are coming into play? What do we think? Anyone to help us? Kunda, what do you think? You're a metallurgist.
First, it's low melting point. Yeah, so it's at the low melting point, quite low metal. So it then becomes useful metal for static bonding.
But do you need diffusion here in this case? When you apply heat, isn't it? So what are you doing basically? So you see this solder, isn't it? This is the solder metal. It's made out of lead and tin. And then when you apply heat to it, it will quickly melt because it has a low melting point, like we said. So it has to be lower than these materials. Imagine if this melted before your solder, so it will end up just ruining your piece. So when it melts, so it's just basically melting. You don't really need diffusion here. So what's happening is that when you apply heat to your solder metal, this is your solder metal. When you apply heat, it begins to melt. And as it's melting, it's covering whatever holes, whatever leaks were on your joint here, for example, in this case. So as you are soldering, it's just simply melting itself and hardening along or on your piece of metal that you want to be worked on. So you don't necessarily need a diffusion property in this case here. Just melting that you're doing, basically just melting and solidification that's happening.
Yeah, just to add on, I think, yes. Mr. Tabo, I think the particle migration is not that of diffusion. It's just melting, and then it covers up whatever is there.
Okay. Maybe it was due to, okay, go ahead.
So, madam, what differentiates this soldering from welding? What differentiates?
What's the difference between soldering and
welding? Yes.
Anyone to give us the difference there?
In fact, that's the reason why I asked you. Because during welding, we find that there's diffusion which is involved.
So how is diffusion involved?
Because there is exchange of atoms, like surface diffusion. In short, there is like formation of an alloy during welding.
Anyone to help us on that one?
I think during welding, I don't know if I can call it the host metal itself. Changes its states from metal to molten or liquid, then it solidifies. So, so the bonding there is quite strong. But when it comes to soldering, you just like
Just melting, yes. You're just simply melting one metal, isn't it? But when it comes to welding, you're actually also melting the base metal. I don't know if you get the difference here. That's like the basic difference, the main difference. So in soldering, you're not melting the base metals. Let's come to our diagram here. You're not melting these metals, isn't it? You're just simply melting this one metal. But when it comes to welding, the process actually involves melting somewhat of your base metal in the areas where you have your heat there directed. I don't know if it's clear enough. Without even going into details, I think that's the main difference.
Okay, I think it's now clear.
Now clear. Okay.
So it can easily detach if an force is applied.
Yes, yes. That's why it's just done in very small pieces of, just in tiny pieces, like you can see, just places where you're not going to apply any force or any stress, like in a phone, just basic materials, just small pieces of material where you don't need to apply any force. Otherwise, it's a very weak joint, actually. It just forms a weak joint, basically, and it can be easily be broken. For example, the motherboard of a computer or a laptop or your phone, you know, that green part with all those small lines, that's soldering. And you know how fragile those are. Even a child can just easily scrape them off with a spoon or something and they'll be out. So they are just more temporal joining.
So, Doc, just a question.
Contribution as well.
Yes.
In other ways, when you are soldering, what you are doing, you are melting the wire and not the metal you are trying to join. The metal you are trying to join will still remain as it is, but then the soldering wire is the one which melts. And then when you are welding, you tend to like melt the base metals using the same one. Yeah.
All right, thank you. Someone had a question?
Yes. I was asking, could it be right? Probably the difference might be the melting points.
Could it be right too?
In respect to the metals being used, the melting point. Because the solder itself melts at probably 200. Then on another metal welding, maybe you might use more than 100, 1000 degrees.
Yes.
So probably, if it is right to say, probably the biggest difference is just the melting point. Because the lower the melting point, I'm sure you might use them in smaller quantities, like devices. Because their temperature in a phone, maybe the temperature of the phone would just reach probably.
Yeah. Yes, precisely. Thank you very much for your contribution. So I hope it's clear to everyone now, the basic difference that we have. Because if the temperature for your flame was lower than the melting point for your base metals, then welding won't happen. So it means your flame has to be at a temperature higher than the melting point, isn't it, of your base metal in welding for you to be called welding. Okay, so we can call it an evening.
Sorry, last one, Doc.
Okay, sure, please, go ahead.
The other question that I wanted to know is the role copper is playing in electric cars.
The role that copper is
playing in, there's this fresh talk about copper in electric cars. So exactly what are we using? What are they using it for in electric cars?
Electric wires.
Electric cars, sorry, electric cars. Electric cars.
Oh, so you're saying in electric cars, why are they using?
Yes. What role is copper really playing in electric cars? Because there's this talk, the current talk about copper, the price of copper going up because of the use of electric cars. I mean, the electric cars. So what exactly is copper used for in electric cars? Is it the body? Is it the components? What components are we using? This is one question of I really wanted to understand.
Okay. So you're saying so you know that the demand for copper has increased because of these hybrid cars and the electric cars, isn't it?
That's the talk which is going on.
Yes, yes. So now copper is being used because it's a conductor of electricity. So when talking about electric cars, you're going to have electric motors there. You're going to have probably an inverter there also. Charging stations also, those will also need copper. So you have your charging stations where these electric cars are charging, isn't it? And so the wiring there will be made out of copper. I don't know, maybe I don't know if I get your question correctly.
Yes, you're right, actually, you're right.
Yes, so it's just that the demand is increased. The demand has increased because of the amount of copper that these electric vehicles are consuming compared to the conventional vehicles that we're using today. The ones that are driven by gas, by oil, by petrol, by diesel, whichever way you call it. I don't know, maybe someone has a better answer than mine.
Actually, it's true. It's the amount of the components that's the side. Because as an electric vehicle, then it means that it's going to use more electrical components than an ordinary. Yes.
So it actually even like it's actually they say that an electrical vehicle, it uses over 7 times the amount of wiring in our conventional gas-powered cars. So you see there's a huge difference there already. That is now before you even come to the charging stations. Just the car itself uses almost 7 times more electrical wiring than our conventional vehicles, the ones that are running on petrol and diesel. So that amount that has increased the demand for copper on a global scale. It's an interesting, this whole electric vehicle arrangement is interesting because, you know, in as much as it sounds